Just do a very quick intro and over to the highlights. So, look, I'm sure everyone saw, at GDC, the epic keynote and with Unreal Engine 5.2, the new Substrate materials. And we're just so fortunate to have Charles and Seb here on the call today, to tell us about some of the vision, some of the tech, and some of the direction here. Both these folks are just absolute experts in the world of materials. Seb, if you're not following him on Twitter, he's always sharing a ton of knowledge in the space. So please do. With that said, Charles or Seb, will one of you do a screen share for your slides?
Yeah, I will screen share that.
Okay, so let me stop my screen share.
All right. So Seb and I are going to present you Substrate, the new or upcoming material system that we have developed for the past year for Unreal Engine. This presentation is relatively short. It's just going to give you like an overview of like the system, and then based on your question after that, we can go in more like a technical detail if you want to. So prior, we started on the Substrate project. Unreal was already providing like a quite competitive like material system based on like fixed shading model. Those shading models were addressing like specific appearance targets, going from like standard surfaces to subsurface, clear coat, clothes, hair, eyes, and things like that. And why not completely adopting like the standard of the art in every technique? It was pretty much like a good implementation of what you could find in the literature and the research. And I guess like the main part of that implementation was like the performance side of it. It was really targeted to be like high performance, being able to run at like 60 Hz on like most of the hardware, and really targeting that realm of like real-time rendering. And to those two part of it, like the wide range of appearance and the target of performance, it was like completing like his role. However, like it was kind of like limited of like the expressiveness due to the targeting and like slotting of the different like shading model, and we wanted to address that. So Substrate was like the bottom line of Substrate was really give artists freedom and being able to expand the appearance range, going from like the standard faces and this like fixed shading model and go beyond that, like being able to target like all those like hero assets that you can see in the movie industry, where you see like tons of layers and like complex emerging behavior from like mixing and compositing matter. And while having like this picture in mind, we still wanted to keep like the core inside, which is like being able to scale from like all hardware and targeting like real-time performances, and being able to get like this like continuum of like parameter expressing the full spectrum of appearance. And so when we started to look at that project, we looked briefly at like what are like the industry look like, is there like any standard that would fit us? And so we briefly looked at like the four major ones, which were at the time like the Autodesk standard surface, which is probably the closest one. When you will see like the core concept is what is appearance. It's a mix between the Autodesk and the Pixel Llama with like all the operators. We looked at an implementation of Material X while diving into the actual technical details, but we quickly backed out from that implementation due to the complexity to scale up and down like material appearance, and we will go in detail about that. And again, like all those framework had like good idea, but like the overall picture was really not matching or constrained of being able to be performant, like 60 Hz and plus, and being able to like store like all those material in a different way, which is like the core inside of Unreal Engine. So the core framework of Substrate is built upon like three pillars, like the notion of slab, which is like how we describe a piece of matter, some operator with which we model and we combine and combine matter, and the tree which represent like the full topology of that matter, like how those operators combine like which piece of matter and so forth. And with these three building blocks, we can express a given appearance. So here's like a quick naive example of like what we can do. We have like two slabs, which express again like two solid pieces of matter. One which is like a conductor, direct conductor with anisotropic fiber. Another one dielectric, translucent, and we just like layer the two of them on top of each other. And from those express of the graph and those two slabs, we can express like a final appearance. So we're going to present you briefly the concept of slab, operators, tree, and how we manage like storage and evaluation. So the matter is defined, as I said, as a slab. So slab is the building blocks of substrates, and it's really made of like two pieces, an interface and a medium. And both are described with properties, and those properties are mapped on like physical properties with proper unit, which allow us to correctly resonate and handle like how operators works. We'll see in detail after that. So the interface is mapping what we see in standard surfaces, like all these like Fresnel values, roughnesses, anisotropy. We have introduced like a dual specular for handling like a haziness and things like that. We have like the traditional like fuzz for like all the clothing and things like that. We have introduced as well like glints and like a custom Fresnel for like mainly targeting car paints, but not only. But with that, a surface is generic enough so that we can describe most of the surfaces, simple surfaces with that framework. The second part of the slab is like the medium part, like the inner piece of the matter. And there we use like a volumetric formulation based on like mean free path and like albedo that allows us to describe how the light propagates into the matter. Again, we use like physical properties with units because it allows us to reach like the full appearance without like not relying on like user transform input or user friendly input. And we'll see how we did with that a bit later. And with this volumetric formulation, we're able to reach like most of like the spectrum of medium, going from fully opaque to fully translucent and this like milky version of it. Again, based on only diffuse and like a mean free path. And for the real-time constraint, we remap like that appearance range into the various like traditional technique from diffuse to subsurface, assuming like dense mean free path and like optically thin, which is something we've introduced, and the full translucency. The diffuse is like implemented with just like a regular rough reflective model, rough reflective diffuse model, and we have like the subsurface, which is implemented with like post-process diffusion or like random walk for the path tracer. We have the optically thin, which is like a pre-computed data so that we can get like the milky look, and the translucency, which is pure like a Beer-Lambert and like interpolation scheme for getting the full spectrum of like appearance again. And with that, like a set of slab and operator, we can manipulate with the operator. We can manipulate like so slab, and that Seb is going to continue on that page.
Yes, thank you, Charles. So as Charles mentioned, you can do a lot with slabs already, but you may want to combine. You want to combine them to create even more advanced materials and effects. Next slide. So we have three operators. One, which is horizontal mixing on the left here. For example, in this example, we mix like some sort of subsurface leather with gold, and we keep all the lobes in the intersection area. So you can see that we can horizontally on the surface mix the two slabs to the two matter. The second operator we have on the middle, it's a vertical layering, which is akin to coating. So in this case, you can see there's a metallic anisotropic bottom slab, and at the top you have some sort of red gel or red plastic that's coated on top of it. And the last operator we have is the coverage weighting operator, which is similar to alpha bending, we could say, basically you may want to reduce the coverage of a surface to make it disappear, basically. Next slide. And it's important to understand, like, when it comes to coverage, transfer process throughput, we use those terms a lot because we think that's the right term in this case. So for instance, in this case, you have like a metallic ball with a glass on top of it, like some glass on top of it. And if transmittance is 0 on the left, you do not see through. Transmittance is set to some dark green color the artist has set up, then you can start to see what's underneath. If the transmitter is set larger, so at least the mean free path will increase, and so you see the bottom layer even more. And if the artists want a part of the surface to be unaffected by the green color of the glass, then it's possible to change its coverage at a macro scale. That's the definition of coverage. So we are not talking about alpha or opacity, or those terms are overloaded and a bit confusing sometimes. So if you talk about in terms of transmittance coverage and throughput which summarize like coverage and transmittance, then you get a better picture of what's going on. And if you, at last but not least, if you set coverage to 0, then of course you do not see the glass layer anymore. So how do we represent such complex adjustment or composition of slabs? So if you look, next slide, please. If you look on this slide, you can see like a bit of a sphere, which has at the bottom part, like a white plastic that is horizontally mixed with gold, like anisotropic gold, and on top of it there's a red gel. You can see that this is represented as a graph of BSDF, so BSDF of slab in this case, exactly. You can see that graph represents the operators, and each time you have the horizontal mixing that is mixing the white plastic and the gold, and on top of it you have the vertical operator that takes them and layer them with the other BSDF. Thank you. And once we have that tree, we can process and evaluate what will be the influence of the top coat onto the BSDF at the bottom. I'm not going into details now, but basically once at the end we know what BSDF is visible, what is the throughput to the view, what is the throughput to the light. We have data to be able to evaluate that. And basically when we're in the shader, we know what which slab will be visible according to their coverage, for instance, or throughput, and we can transform that into closure that then are going to be evaluated. So if we are using forward shading, then we evaluate the lighting like in the shader in place. But if we are using deferred shading, which is definitely more complex case, then we have to write that out. So we have some. Without going into details, I will detail a bit more after, but we have some simple, super fast paths, which are only writing 12 bytes per pixel. And the more you add features on slab, then you will write more. You will go into the single case, which has like a slab with more features. And if you have multiple slabs, you will go into the complex case. And if you use some more advanced features, such as glints, then it's going to be an even more expensive path. And all this shows that we're not talking about optimization here. We just show that, okay, for different platforms, that may not fly. So we have to think about a way to adapt the material to a target platform. So next slide, please. What we do for that is, because we are in a real-time context, we are in the game industry, so we need to make sure we run across, like Unreal Engine, just to remind you, is running on mobile, on Switch, on the console, PlayStation and Xbox, and also PC. So we want to adapt the material on those different platforms, for instance, and for that, but we only have a complex tree, as you see. So on the left part, you can see this is like 72 bytes per pixel to evaluate, to store, sorry, the closure. But if we, let's say we want to run that on console, maybe we can only afford 50 bytes. I'm just making numbers. So basically, what we propose in this case is to basically collapse operators and to parameter blend the slabs into the slabs evaluation into a single other slab, basically, or closure. So in that middle part, we only end up with 2 slabs, which are at the bottom of the tree, and then once that's the bottom and one that's at the top, and we only keep the vertical operator. We try to start by simplifying the BSDFs that are deeper into the topology. And last but not the least, you can also fully simplify the full graph into a single BSDF. Of course, now you can see that it's a bit more visible that there are some differences, but it still maintains some coherent look, which is interesting for only 12 bytes as compared to the 72 bytes originally. But basically, that should be able to run on mobile then. So that's the simplification scheme we have in place. And if that doesn't still fit, we can like simplify features, for example, remove SSS or this kind of thing. So that's how we want to scale. And that is the scalability is set up per platform. We decide what you want to do per platform. But once that is done, then let's have a look at how we execute the lighting and all of that at runtime. So as I mentioned, so we have different complexity, and we want you to pay only for what you effectively used at runtime. So if you have a simple material, you should not allocate too much memory to store that material, or you shouldn't run the complex shader to leave that material. So that's why it should always adapt to what you have. But you should have fast path for the console, but also Hero Advanced material should work out of the box. So in the rasterization path, what happens is basically when we compile the material shader, we know what can be removed, for example, if something that's been removed from a platform, for instance. Then when the material executes on the shader, as a pixel shader on the GPU, then we know, for example, our coverage of this material, of this slab is 0, so it can be removed. So technically, we can prune out like slabs dynamically. So you can see that at the top right here, there's two materials being blended horizontally, mixed together: a green plastic and some yellow metal. You can see that on the tile classification only show complex tiles where the two slabs are visible, are present basically. So you will only pay the cost of the complex evaluation of two slabs on those tiles, and then all the other tiles will go the fast path for basically just a diffuse and specular, basically. So that shows like that the base path shader, when it writes those data, will adapt dynamically to the input. Sorry, and you can see that we classify. So here we can see complex and simple, but we also have a single, which is a slab with a bit more features, like for example F90 or SSS. And with the classification that you can see also at the bottom a bit more varying various classification on the screen. All those styles are super important so that we know the complexity of shader we are going to dispatch, for example, for the lighting, or lumen, or for the subsurface passes. We know which tiles need subsurface, we know which subsurface it is and what complexity it's going to be. And that's important for like basically, there will be less code executed, there will be less VGPR allocated for example, in the simple case, it's going to be a lot faster. That's important for our performance, as mentioned at the beginning. We run some game at 120 Hz. So the path tracer, however, is a bit different. So in the path tracer, we cast array, and in the heat shader, if you know a bit how it works, with heat shader, we can evaluate the material, and so we can have a list of all the slabs that all the closures, you could say, that needs to be evaluated. But for the path tracer, we cannot send that directly back to the red generation shader, because that would be a huge payload and it will slow down everything. So we just stochastically select one closure to be evaluated based on its effective directional albedo to the view. And basically, we build up the frame like that, stochastically evaluating slab per slab for each pixel, for each intersection. I think that's it for this slide. So just a little bit of high candy, why not? So the first one is that material I showed you before, which is the bottom slide with an isotropic lighting. Then you color it with a colored coat. That was already not possible in Unreal to have a colored coat, or not controllable this way with any color, and changing the bottom color and the colored coat independently. And then you can have some dust on top of it layered also again, so that was even less possible in Unreal. And you can keep all the loops effectively for the advanced use cases. As Charles mentioned, we've shipped, or as it has been mentioned already, as Patrick showed already, we have shipped like the Opal demo, and this is like the Opal material. So inside there's at the bottom layer there's like two slabs with some relief mapping parallax effect to give a sense of depth. And then on top of that you have the clear coat of the car, and then dirt and dust also. And the last one is just, so this may look like some basic materials, but in fact, it's a bit more advanced. Like those are like some advanced, like we could say car paint, for instance. that has like some glints, and on top of the glint, there's a colored code, which maybe has transmittance, a bit of scattering in it also. And on top of that, you have some like the clear code, you have the specular. And in this case, you can control, of course, like all the roughness, and we even have like pearlescence effect, subtle pearlescence effect. Maybe you can spot it in some places because that is possible with the specular lookup table that we have now. The advanced thing. So it looks like simple material, but inside it has lots in it. So basically that's it. So let's conclude a bit, and let's start with the interoperability. So with open standards, so that is achieved in Unreal Engine through Datasmith. And right now, this does not leverage a Substrate yet, but of course that's a goal. When that will work, so we expect features to map one-to-one, like specular or diffuse or maybe subsurface, anisotropy, except maybe if you use the macro self-tested distribution that is not GGX, that we don't have, we only focus on GGX. There's also, when it comes to Disney and standard surface, we believe that this can be efficiently mapped to our representation. However, when it comes to a soup of PSDF, for example, Material X, which has like a diffuse there and a specular there and another specular there and another like something different, that all those can be layered differently, then it will have to be a series of slab and operators. Maybe we can recognize some that are specular and diffuse and merge them in a single slab. But basically, then if you go this way, then the import-export is not going to be identity also. Yeah. So we should be able to get to somewhere, but it's not going to be identity and back and forth translations. So to conclude, this is what we believe is like a modern material framework that is also built with like performance and scalability in mind. So yeah, built of like slabs, operators, and the tree and all that we can simplify or not, depending on the platform you want to run. And it has like all the advanced features that you expect for a modern material framework, also like haziness, multiple specular loads, specular load for pearlescence, glint transdrawing, and the support in Unreal Engine, we already like support all the systems, and most of the platform is coming basically. And the timeline is, so have you seen, we've shipped like the electric drills demo at GDC, and next it's going to be about focusing on production readiness for games, so performance and memory, which is in a good state, but there's still things to do. Yeah, still things to do. Yeah, I think that's it. Thank you.
Me, no, that was awesome. You guys took us through a lot of material, and I loved all the focus on the performance and the rationale. I'm sure there's going to be a ton of questions, and I see Guy has his hand up first. So Guy.
Sorry, only for the notes. Can we go back to the interoperability slide and cover that a little bit more, since it is relevant to this group? So kind of, can you walk me through it in a little more detail where you think the interoperability with things like Material X and other things can happen? Maybe I missed it as you were going through.
So as Seb mentioned, so we have this like Datasmith system which can ingest like different like file format or different formats and like ingest that into what Unreal can interpret for material geometry and so forth. So at that translation level, we already have something that can convert like Material X to Unreal material. So the goal is to have the same for substrates, except that with substrates, because we can have like a wider expression of appearance through like composition, thing like that, we will be able to represent like more faithfully those like advanced material in Unreal. The mapping again won't be one-to-one, but since like the concepts are fairly similar when you looked at like the open standards, there's like a good chance we can nearly map one-to-one and we express as we import, and maybe as we export, like we export something close to what was imported. That makes sense.
Yeah. Okay. So what you're saying is you're going to get basically additional properties, additional things within this after you import from a Material X node that won't be able to define all of the cool things you guys are adding with the substrate. Is that a fair statement?
So we will be able to ingest like probably all what standard material expressed, And then once you have that material, the user is free to add and modify it. And there, yeah, maybe if there's some features that are not supported, you can add it more. When we export, then we're going to trim down to what the standard for which we export to supports. But yeah, that's
okay.
mainly,
That makes sense. Thank you.
Yeah, okay.
No, that's good. I'm good. Thank you.
Okay, cool.
Great. Other questions?
So if you're interested, we're going to have a talk in SIGGRAPH which go into way more technical details. That's going to be at the advanced rendering real-time rendering techniques. And then we go into the actual like nitty detail. Here we again give you just like the broad overview of the concepts, but like there's many things we can dive into. So if you have technical question as well, you feel free to ask as well.
Mm-hmm.
Cool. Yeah, I think many of us will be at SIGGRAPH, and your talk in advances in real-time rendering sounds great. I wanted to ask, I mean, since this has been in beta, what type of feedback you're getting from users and artists?
Yeah, we're getting all sorts of feedback, like some people very enthusiastic, like some already people using it to do like crazy stuff. We get like bugs feedback also. So that's interesting. That's good. We have a forum where we receive like bugs from users. So some users, well, yeah, we also understand that actually user artists are also like there's a new way to build up materials, and that's a bit advanced. So sometimes it's a bit confusing for artists. We have noted, but we are working on it. It's a big task actually, and yeah. So we are seeing some. If you search on Twitter or Google, you can find some advanced use case already of that.
Yeah, we're working with like a few like game partner and things like that, but as well like movie industry, and those people are super happy about that because it feels like more something they're used to, and they can express more what they want. And so, for instance, like the people from WEDA, with who we work, usually like they like can already leverage quite a bit like all this tech like in a great fashion. So that's good to see. But as Sébastien said, like so if you use like the raw concept of Substrate, it can be hard because like making sense of like free path and things like that is not super easy. So we have added like at the UX level many nodes that can help or abstract those concepts so that we can reach more like casual users. But definitely there's like some education gap that needs to be happening the same way we transit from like non-PBR to PBR. There was like a full language and education happening. I guess like that a bit the same, like getting like interested user more into those concepts. That's something that needs to happen as well.
So are you guys interested in turning this into some kind of an open standard?
We have been asked about that in the past, and there's no willing for that. It's more like we would like to maybe, I don't know, inspire a bit like some standards so that like we go a bit toward that, especially around the simplification and things like that. But there's no desire to, at the moment at least, to formalize that into standards.
Yes.
How about for supporting Interop from other systems?
So can you say that again? Sorry.
Yes. So obviously Substrate is going to operate inside of Unreal. What if people want to author assets elsewhere and take advantage of the full set of capabilities that Substrate provides? Are you going to make it well enough specified so that it would be easy for people to create tools outside of Unreal that would translate easily one-to-one for import and for export?
Yeah. I mean, I believe we can specify it completely. I don't know if that's making it like a standard. I don't think, but specifying it, yes, it can be specified. Yeah, definitely.
I mean, for example, one way to interop would be to express each of these different concepts that you've described inside of MDL.
Yeah, I believe that's possible already. A lot of them already. yes.
So would you guys
I
be
think-
supportive of an effort like that? I mean, you don't have to answer right now. That's a bit, maybe a rhetorical question you can go back and think about.
Yeah,
Yeah, but
that sounds good.
there's yeah, I don't think that's a problem. I think that's good.
Other questions or comments? So there's a few folks on the call that work on PBR materials for GLTF. So there's Ben Houston here, then Henrik from Autodesk. I guess I wanted to ask them if there's any inspiration here, because it's interesting to hear you guys say Unreal is used primarily for real time, and you're looking to make more movie type workflows, so kind of adding a level of complexity in order to allow more capability and flexibility, but then you're distilling it down into something that's really efficient for real time. So Ben, I don't know if you got any ideas, just from this.
Yeah, well, I've actually mentioned it before, even a couple months ago when I did the presentation on PBR to this group. I think that this and Pixar's Llama, something like that is probably should end up like where GLTF is going to evolve to in like within 2 years. Because I do think this is sort of like you guys are leaving the state of the art in real time. Pixar is doing it at sort of the movie industry. So this is, yeah, I do think we sort of come full circle. I don't know if anyone remembers, but before PBR, we used to have all these little bit of layers, right? We have a glossy layer, and then we would make like 2 or 3 lobes out of them. Then we went to a single unified material. Now we're splitting that up into new composable materials again, but they're sort of at a higher, more physical level. So I do think GLTF will probably follow. That's my thoughts.
Yeah, and I think just the simplification, steps to target multiple different levels of fidelity. That's something that we've been very interested in doing for standard surface and have a little bit more well defined. But we haven't really done much work in recent years. So I think there's definitely learnings, from this work that we could incorporate there. And of course, we have work going on between Autodesk and Adobe there and Line. So hopefully some of the things that you kind of solve here to target like all these different kind of capability tiers, that's something that we could all align on a little bit better.
Oh, when I mentioned history, what happened is Disney introduced PBR in Tangled, I believe. And then Unreal Engine with Unreal Engine 4, they introduced PBR at real time. Brian Karras, I believe, did all the presentations. And then both industries sort of moved to PBR at the same time. Well, maybe we're just doing it again. Feels like it.
Take that as a compliment.
Other questions or discussion? I see in the chat here, Nick mentioned that Lem is from Industrial Light and Magic, and then Nick, if I could put you on the spot, is there any ideas here from a USD perspective or anything that came to mind?
The question in my mind is probably the most obvious one, which is that, well, obvious to someone who works on USD, which is that we've got USD shade graph, and I was trying to parse mentally if I am able to concoct a graph that corresponds to the constructions that were shown in USD shade graph already, or if it's necessary to introduce extensions to carry it further. I was also quite interested in the facility for targeting deferred shading as well as forward shading, which is something that, for example, Hydra doesn't really offer through Storm at the moment. And so like the puzzle of the closures that work both ways is really fascinating to me. So mostly it's got a lot of ideas bubbling in my mind, and I don't have anything particularly to say beyond that.
We can talk more about it later, maybe. I'll see.
Cool. Okay. Well, it sounds like SIGGRAPH. Coming to the SIGGRAPH talk. Nicholas, I see you have your hand up.
Yeah, just a practical question. Is it available already in some version of Unreal? Because I didn't saw this stuff.
Yeah, it's available in 5.2, so it's experimental.
Oh, in
meaning
5.2, okay.
Yeah, in 5.2, yes.
We are not in 5.2 yet. It's why.
Right.
Yeah.
Yeah, you need to opt in at the project level. It's going to switch all your shaders. They auto convert everything in the back, but then you have access to the new capabilities and you can create new material with what we show.
Okay, I will check. This is very interesting. Seriously, congrats. Very well made.
Thank you.
Other questions? So maybe just a question from me in terms of editor versus runtime, right? So is all like how much of the baking when you mentioned, hey, if a parameter is static, you go do an optimization, or something's dynamic, but it's within a range, you kind of combine things. How much of that is done like editor time versus at runtime in a game?
So yeah, Seb, do you want to go for it?
I don't know whatever. Yeah, but on the compiler side, when we translate the material graph, we can see what branch should be removed. Let's say one is only for one platform. If it's one platform, one is used only for example, for fast tracing side, if there's some specific artist, things like that. But otherwise, we always consider the worst tree for the material. Let's say there's we don't detect that, I think, yet, but we could detect if there's a specific constant set to 0 in a weight, then we can see what's going on. But other than that, if there's a texture is red, we cannot do anything. We have to evaluate and see that at runtime always. So we often have like we have the worst case graph that's constructed for the tree, I mean, for the material graph, and that we know how we have to parse, what we have to parse. So that's an interesting problem is the compiling cost of like the compilation cost of such a shader, because you cannot do pre-parsing in a shader. It's like the compiler just crashes sometimes. So we had to basically flatten that parsing with function calls and everything. And so in this case, yeah, and once that's done, then the compiler also, when it compiles, it will recognize if there's some values that are 0 or 1. For example, if we disable some features, so some features are also, some evaluations are also automatically removed by the compiler. But other than that, it's going to be all dynamic here.
Gotcha. Yeah, super interesting.
And to mention like the simplification we mentioned as well. So like what Seb mentioned is what like for a given tree, but like the simplification of the tree is done on the editor/compiler side. So if we target like, for instance, like a switch, and we're going to simplify everything into a single slab, for instance, that simplification is done like once statically in the editor, and then at runtime you don't pay for still like reducing this tree and so forth. That makes sense.
Yes. The compiler will not be able to do that. The HLSL compiler.
Yeah. And like all this, like one thing we didn't mention is like all this like a simplification at the moment are done through rule base. So we determine like a few set of rules, and based on those rules, then the simplification happen. There is no overall fitting or any machine learning or like anything magic over there. It's like rule based. Which means that like most of the time it's going to reduce that into a coherent set of appearance. But since some parameters are dynamic, we don't know all the parameters, doing like a reduction or like a filling is really hard, because we only partially know like what the end result should be, because again, we have only the topology, a few set of like, it might add this like input range and give that, but all the simplification is based on those like abstract rules.
Very cool. So Seb and Charles, I mean, look, this was really exciting, and just the way you're pushing the limits and advance in real time here, I think is awesome, and also a very good foreshadowing your SIGGRAPH talk. I'm sure you'll see many of us there. So thank you both for coming, and please when you have a chance, please send me your slides if you haven't already. I'd love to share with our group. And then this
Yes.